Hello everyone! Welcome back to the Secrets of Calculus. Today's episode will complete our big brain toolbox of derivatives of quote-unquote standard functions. Hang on, is this video too long for you? Here's the formulas. Yeah, once again, there's a lot of them. Let me know what you did with that extra free time. So far, we have made this alpine slide much safer by having a smooth slope at the top that gets steeper in the middle and then smooths out again at the bottom. This is a great start, but the slide is still moving too fast. We need to put in some bumps, which we can model with trig functions. But once again, we need a way to find out how fast the sled is going at any given time, which we can do by taking the derivative. Let's start by introducing the smartest guy in the world, SOHCAHTOA. He knows everything that has to do with anything related to trig. Now, SOHCAHTOA says that the sine of an angle is the ratio between the opposite side and hypotenuse. And yes, by the end of all this, we will all be high on hypotenuse. So when this angle changes, like what you get with the function sine of x, you're actually keeping track of a fraction with two changing values. To keep things simple, we'll put our angles on a unit circle, so our hypotenuse will always be 1. Now, when the angle changes, the opposite side changes with it. The question is, how much? Let's put the function sine of x into our limit definition and see what happens. Well, it looks like it's time for Trig Tricks! We can use the angle addition trick to deal with the sine of x plus h part. And now we can split the fraction and the limit across the addition. Now in both limits, only h is considered, so we can move the sine of x and cosine of x parts outside their limits. Oh boy, these limits are unruly, and there's no big brain way to solve them yet. So we need to brute force these limits by letting h get small. Let's start with the first limit. And we don't have to go too far to see that this limit seems to approach 0. So we can throw away the entire sine of x part. The second limit is one of those special limits that, for now, you're going to have to trust me that it equals 1. We'll learn how to work with these, but for now, just trust me. So there we go. The derivative of sine of x is cosine of x. We can do the same thing with cosine of x. And there's some trig tricks we can use for the cosine as well. Now the great part here is that we already know what these limits are. The limit as h approaches 0 of cosine of h minus 1 all that over h is 0, and the limit as h approaches 0 of sine of h over h is 1. So the derivative of cosine of x is negative sine of x. We've gone back and forth, and now we can assemble what I call the square of J. But that's just sine and cosine. What about the TOA part of SOHCAHTOA? The tangent function is literally just the sine over the cosine. Unlike sine and cosine, where you have to go inside the parentheses to convert from one to the other, tangent is honestly kind of pointless because you can just divide them. Later, we'll talk about how to handle quotients inside your derivative. But for now, we will do a big brain derivative lightning round! The derivative of tangent of x is secant squared of x. And this, by the way, is one of the few times that we bring up SOHCAHTOA's brother, CHOSHAKAO. This is partly because CHOSHAKAO is always in the shadow of SOHCAHTOA. The derivative of secant of x is also one of those functions that is the derivative of itself, but it has a multiplier of tangent of x. And you know how sine and cosine are so linked with the derivative, as are tangent and secant? Well, cosecant and cotangent are also so linked in this way. The derivative of cosecant of x is negative cotangent of x times cosecant of x, and the derivative of cotangent of x is negative cosecant squared of x. Now, all that is going to be irrelevant once we cover the quotient rule next episode, and in fact, it's honestly kind of irrelevant no matter what. Just remember,
the square of J.
and you're good to go. What about the inverse trig functions? These get really weird. And the explanation for where these come from uses implicit differentiation, which will be covered at another time. But we can assemble everything up to that point, starting with arc sine of x. If we say that y equals arc sine of x, then that really means x equals sine of y. One thing that is really useful is this trig trick. Sine squared of y plus cosine squared of y equals 1. This, by the way, is gathered from the Pythagorean theorem on a unit circle. Rearranging slightly, we get cosine squared of y equals 1 minus sine squared of y, or cosine of y equals the square root of 1 minus sine squared of y. We know from above that x equals sine of y. So plugging this in gets cosine of y equals the square root of 1 minus x squared. Now here, we jump into magic land, and I'm going to say that the implicit differentiation part basically says that the derivative of arc sine of x is 1 over cosine of y. And so, the derivative of arc sine of x is 1 over the square root of 1 minus x squared. It's a weird one. And we can do the same thing for arc cosine of x. If y equals arc cosine of x, then x equals the cosine of y. Using our trig trick, we get that sine squared of y equals 1 minus cosine squared of y, or sine of y equals the square root of 1 minus cosine squared of y. And since x equals cosine of y, sine of y equals the square root of 1 minus x squared. The implicit differentiation part says that the derivative of arc cosine of x equals negative 1 over sine of y. So the derivative of arc cosine of x is negative 1 over the square root of 1 minus x squared. You can probably see a pattern with this implicit differentiation stuff. And now for the other trig functions. And we can't do a lightning round because the inverses mess everything up. And you can't just divide arc sine and arc cosine to get arc tangent. But it's a similar strategy. If we say y equals arc tangent of x, then x equals the tangent of y. There's a trig trick that lets us convert from tangent to secant. That's secant squared of y minus tangent squared of y equals 1. This, by the way, comes from taking the sine and cosine trig trick and dividing by cosine squared of x. See, tangent and secant are not that useful. Rearranging slightly gets secant squared of y equals 1 plus tangent squared of y, which further gets us secant squared of y equals 1 plus x squared, because we said that x equals tangent of y. The implicit differentiation part tells us that the derivative of arc tangent of x is 1 over secant squared of y. And putting it all together, we get that the derivative of arc tangent of x is 1 over 1 plus x squared. We can do this for arc secant as well. If we say that y equals arc secant of x, then x equals the secant of y, then we use our trig trick for the tangent and secant pairs, which gets us tangent squared of y equals negative 1 plus secant squared of y, or tangent of y equals the square root of x squared minus 1. Implicit differentiation says that the derivative of arc secant is 1 over secant of y times tangent of y. We know that the tangent of y is the square root of x squared minus 1, and we've stated that x equals the secant of y. Putting it all together, we get that the derivative of arc secant of x is 1 over x times the square root of x squared minus 1. And because arc secant is weird, we actually need the absolute value of x here, instead of just x. Whew, we're down to the last two functions. Same idea, just now we're using the trig trick that cosecant squared of y minus cotangent squared of y equals 1. Which, by the way, you get by dividing the sine and cosine trig trick by sine squared of y. And since the process is so similar, I'll just super speed through this. And once again, we need an absolute value on x here as well to get the derivative of arc cosecant of x. Okay, speaking of which, side step here. The derivative of arc cosecant sounds like something that someone trying to sound smart would say. All you gotta now say is it's the quantum derivative of cosecant, and then you get what a Marvel character would say to explain away the plot holes. Okay, sidestep over. Last function, the arc cotangent. Super speed! And there we go. We now have the full collection of trig derivatives, and there are no more trig functions out there. I said, okay, but that's going to have to be a separate video, because this is already too long. Also, hyperbolic trig is not used much, so it's actually going to be in the miscellaneous tidbits section. But now we have the full collection of all big brain derivatives of quote-unquote basic functions. Next episode, we're going to fully break away from the limit definition as we go into the product rule and the quotient rule. You've already seen how useful they would be. Try proving some of these derivatives yourself. See you next time! The quantum derivative of the eigenarc cosecant. I swear that's something Tony Stark said once.